Welcome to our webinar. Today we are going to talk about a really cool, I guess we call them ECMs, energy conservation measure. It's a really cool ECM, which is, let's just say, it's one of these new things that's going to be that very well could revolutionize what's going on in our, in the ESCO industry. We're always looking for what's new. We had LEDs, we've been living on LEDs for so damn long, but everybody's got them now. So what's the new technology? Well, there's AI, that's one of them, but I think this is another one. So I thought that you should give a listen to Eli, and why don't you change the slide, Eli? Yeah, that's me, and that's Eli. This is when Eli looked a little more clean cut than he does now. So Eli is the, I like your current picture better than this one. He is the CEO and co-founder of SkyCool Systems, and they're based in the Bay Area. And I'm not gonna, I'll tell you why I know about them. So I was, one of our contractors, his name's Kazim. He is just absolutely brilliant. He's a walking, not just encyclopedia, he's an encyclopedia that keeps updating every day and always learning what is the newest thing, what's the newest thing, and he knows everything. And one of the ECMs he came up with on one of our projects was a SkyCool system. So I looked into it like, what is this? And that's where I learned about all this. And I thought, well, this is really cool. And I think this is something people should hear about. That's why Eli's here. And just one other thing, Abraxas, I never met Eli or SkyCool people. We don't make any money off of this. I don't care. I don't care. I want this stuff to work because I'm always looking for what's new, but we don't make any money off this. This is all about just showing you what is new out there. Anyway, so Eli is going to introduce himself, and I'm going to disappear, but I will interject if I don't know, decide to. Talk to you later.
Cool, thank you, John. Yeah, appreciate the opportunity to talk about what we're doing. My name is Eli. My background's in mechanical engineering. I went to Stanford for grad school and then did a PhD, postdoc, excuse me, and that's where I started working on this technology with co-founders. But the whole idea or premise is a way of passively cooling our planet. So we've created a novel material that doesn't get hot when it's outside and under the sun. And in fact, it can be cooler than the air temperature, cooler than the ambient air temperature, even under direct sunlight. And it can cool during the day and at night. And I'll explain in this presentation how it works and what we're doing with it. But we are developing products using this core tech to save energy for cooling. And so with that, so this past summer, we hit a pretty big milestone. The planet was the hottest it has ever been, and every summer moving forward will likely be hot or get hotter. And so what does this actually mean for you guys as you think about building and sizing cooling systems? It means it's going to be harder to predict, peak temperatures and how big to make things. It's going to mean existing equipment is going to start to underperform. You're going to have condensers that aren't able to reject heat because it's not designed for the temperatures essentially that we're experiencing today. Evaporative condensers will use more water. We're going to start to see evaporative condensers that can't be installed in certain regions. So for example, in Las Vegas and Phoenix, already there are moratoriums on using these types of systems because they're water stressed. And then as we switch to new refrigerants, there's going to be more transcritical hours, specifically, for example, with CO2, and this is going to mean more power and more energy use in these systems. There's for sure the opportunity to use sprinklers in underperforming equipment, like these underperforming air-cooled systems, but that does lead to corrosion and other challenges. And so at SkyCool, we're trying to use our core technology, these cooling panels, which I'm going to talk about today, to essentially add modular heat rejection to improve the capacity of existing equipment of condensers. It will save energy. It reduces the demand for a cooling system in the summer. These panels can essentially reject heat without water, and that's again through this core technology that we developed. The panels can reject heat not only during the day when the sun is up, but also at night. They don't use the sun They actually use the sky, and I'll get into exactly how that works in a little bit. But we like to think of these as a way to improve heat rejection. You know, there's only one moving part. It's a pump, which we use to circulate fluid through these panels. And so it is reasonably simple. And it's refrigerant agnostic. It doesn't matter if you're using an HFC today or CO2, or you just have a heat load and you need something to be cool. So I will go into the specifics in a little bit. In order to really understand how these panels work and how we're cooling, it's helpful to think about how our planet, the energy balance on our planet. And so essentially, you know, all of the energy comes into our planet from the sun. It heats the planet. At the same time, though, there's cooling that occurs. And if this cooling effect didn't happen, our planet would be too hot and we would all likely die or not exist. But what essentially happens is the Earth is emitting infrared light to the upper atmosphere. It's easier to experience this at night, but it's also occurring during the day. At night, it has a name called night sky cooling. But essentially, if you've ever seen frost on a windshield of a car that's been parked outside, or you know, seen frost on a roof of a building, it's because of this effect. And so what SkyCool is doing is essentially tapping into this cooling effect. We've been able to make this film, a material that simultaneously can reflect energy from the sun, so it doesn't get hot from the sunlight, but it can at the same time emit this heat to this cold sky. And so we've created this ability to have this night sky cooling effect occur during the day. And so this is kind of abstract, but in practical, you know, sort of observations, you know, we can take a surface. This is a material that was placed in an electronics box in Death Valley in California. But essentially, you know, the surface of our box, of our film, was about 10 degrees cooler than the ambient in the middle of the day. This is from 9 to 5 p.m. You can see the ambient on this day was around 115 degrees at peak, and then, you know, relative to, you know, a white coated box, it's around 40 degrees cooler than that surface. And so this is what our core technology can do. It's really just the ability to keep a surface cool. And so at SkyCool, we're developing products that use this material to reduce energy use for cooling. The first product is this cooling panel that I mentioned. We're also using the material to make a roof, which I'm not going to talk about today, but happy to answer questions on if there's interest. But the product for today's conversation is a cooling panel. It essentially has pipes on the back of it, like you can see in this graphic, and we are able to flow water through it. The water comes in hot, it leaves cold, so it's very similar to a solar hot water heater panel, solar hot water heating panel, except it's the opposite. You know, we pump hot water in, it gets cold, and we use glycol in our panels. The water circulates through the panels, and then it goes into heat exchangers, which are used to either subcool or pre-cool or desuperheat refrigerant in you know, vapor compression cycles. So these would be air conditioners or refrigeration systems in commercial or industrial refrigeration systems. But you can see, you know, generally the integration here. So these are compressors for a supermarket refrigeration system where they have, you know, low temperature cases and medium temperature cases, or temperature groups, excuse me. We have the pre-cooling heat exchanger, which cools refrigerant before it enters the condenser after the compressors. And then we have a subcooling heat exchanger, which essentially cools refrigerant after it leaves the condenser. And both have value, which I can explain in a couple slides. But the end result is that they either provide capacity as a pre-cooler in the summer, or energy efficiency as a subcooler. Generally, we're interfacing the system with heat exchangers. So we use raised plate heat exchangers. These are relatively common in cooling systems, but in terms of the installation of the heat exchanger, it takes, you know, around 2 hours. A lot of the prep work is done before cutting in, and then it's just essentially brazing in the pipe. But it's essentially the way that we're using the fluid that's cold from our panels to cool refrigerant in these different cooling systems. And then in terms of the broader system installation, it really depends on how many panels we're putting in, but it might take between 3 and 5 days to install an array. And then maybe the only other point to make here is the system is in general refrigerant agnostic. You maybe potentially switch the heat exchanger out if you had a high pressure refrigerant versus a low pressure refrigerant, but that's a relatively low cost from the installation perspective. So subcooling is one way to save energy in a refrigeration system or cooling system, and it essentially involves cooling refrigerant after it leaves the condenser. So typically the refrigerant leaves a condenser as a saturated liquid, and essentially subcooling is cooling that liquid as much as we can. It adds capacity to the liquid when it gets expanded in cases inside the system or after the expansion valve in the evaporators. And it's a way to essentially add between 15 to 20% efficiency to a cycle, and it's really going to be dependent on how much cooling you can provide. As a general rule of thumb, for every degree Fahrenheit of subcooling that you can provide, you're going to add 0.5 to 1% efficiency to the refrigeration cycle, and the variance is really driven by the refrigerant type and the evaporator temperature, the suction pressure for the system. But you can see here some general data that we've been collecting. It is somewhat noisy, but this is from a refrigeration system where we've been able to add refrigerant, and we isolated the data to show that the power essentially reduced as we added more subcooling in to the system. Pre-cooling is essentially reducing the load on the condenser, but it's going to be more impactful to the energy use of the cooling system when the existing condenser is underperforming or it's at a limit where it's no longer able to reject enough heat from the refrigeration or cooling cycle. And so pre-cooling or desuperheating essentially is cooling the refrigerant after the hot discharge gas leaves the compressors. So it essentially allows the refrigerant to come into the condenser close to the saturation condensing pressure and temperature. In the case of underperforming condensers, essentially we're able to lower the discharge pressure for the system. And so you can see data, this is discharge pressure from a store in the Midwest, but essentially this condenser was underperforming. They've added cases, so there's a lot more heat that it needs to reject. They've added sprinklers to the system, so it's also got a little bit of corrosion on it. But anyway, by adding the panels, we're essentially able to lower the discharge pressure, and that allowed the system to operate actually at higher temperatures, higher ambient temperatures. Previously, it would shut down, and they'd have issues with compressors locking out when the discharge pressure went above 380 psi. But in the context of HFC cooling systems, so 410A, 404A, it will save energy, it adds capacity. In the case of evaporative condensers, it's a way to reduce water usage. And so I'll talk about a case study where we installed this with an evaporative condenser, and we're able to reduce water usage by about 40%. And then in CO2 refrigeration systems, so these are transcritical refrigeration cycles, we're able to reduce the number of hours where the system went transcritical in its operation. In data centers, there's a slightly different integration that we would present. We haven't done this in the field, but this is going to be. I'll talk about the data center case study that we made. It's more modeled than actually built. But the idea in data centers is there's an opportunity to improve the efficiency of the chillers in the hot times of the year by subcooling, and then in the cooler times you can use the panels as essentially free cooling. And it would essentially replace a dry cooler, which is essentially a way to use ambient air to cool a chilled water loop. But instead of using a dry cooler with fans and a pump, we would just use our panels to directly cool the chilled water loop. And so you can see in this case, this would be a place or a facility that has end chillers. And in this case, we're just modifying chiller number 2. But in cooler times, we're essentially gonna add bypass valves into the return chilled water system to this chiller, and cool that water loop with our array when we can, and that can essentially have a much better energy savings in the lower ambient conditions. And then when it's hotter outside, we can subcool the chiller. So unlike dry coolers, which typically just sit idle during hot times, we can provide value to the chiller by subcooling it, and that adds efficiency, as much as 15% for the cooling cycle. So, cool. There are lots of different integration modes with data centers. Data centers are all somewhat unique. These are just a number of different designs that we've thought about. But there's immersion data centers, which you're starting to see, where you have direct liquid cooling of computers, and that's maybe what you're seeing in this top right corner. But the panels can be used to essentially directly cool the fluids in these pods or immersion tanks. You can combine the system with crack units or water source cooling units, essentially using the panels to directly cool a condenser or replace a condenser, and then they can economize by directly cooling the air when it's cooler outside. And then you can use it for the direct cooling, which I just mentioned. We have a chilled water loop, and the panels are just cooling the water circulating through the system. In terms of how, I talk about how these panels work. They work by essentially rejecting heat to the upper atmosphere of the sky. But the heat rejection performance is going to depend on a number of different variables. So it'll depend on how hot it is outside, how much energy from the sun we get. So that's the solar radiance. It'll depend on how hot the fluid is relative to the ambient air temperature, how dry the atmosphere is. Drier climates will perform better than humid climates. And certainly if there's wind, for example, you'll get more convective heat rejection than if it was, say, not windy. This is a renewable technology. Clouds will influence the performance. Higher clouds tend to be colder, and so they don't impact performance as much because they're still cold, just like the sky. The hardest operating conditions would be low fog, and so Seattle, Washington wouldn't be the first place I would want to do a deployment, just because the fog is really low. It's typically warmer than high clouds or even the blue sky, and so that reduces the performance by as much as 40 or 50%. And then the other sort of thing just to acknowledge is usually when it's cloudy outside, cooling loads are lower, and so in general the air is lower, and so you can balance some of the heat rejection. Instead of radiation, it goes by convection to the local atmosphere. But we don't tend to see too much of a performance variation with panel systems in most locations. In terms of the surface, part of the reason this works is because the material that we've developed is very reflective of energy from the sun. And so keeping the panels clean is really the primary maintenance that needs to be done for this system. And so that will reduce performance. And so typically in these systems, we recommend cleaning the panels, a couple times in the summer when it's dry outside. And so we have a process so we can see, when the panels get dirty from the data, and we can trigger essentially a panel cleaning using local solar panel cleaning crews. So I have a number of case studies from sites that we've deployed at. We've done about 16 projects to date. Most of these are going to be, so all of these case studies will be from supermarket refrigeration systems as a way to save energy and provide capacity. One of the sites is going to be an HFC refrigeration system, so it uses R404A, so it's a more traditional cooling cycle. We have one set of case studies with CO2 as the refrigerant, so these are transcritical CO2 systems, and then one evaporative cooling case study where we installed water sensors or sensors to measure how much water the condenser is using, and then quantified how much water savings we had from our system. And then I have a case study from a data center that we put together, and I can talk about the integration potential there. So this is a site in Northern California. You can see our arrays in the bottom right over here. You can see there's solar panels on this roof as well. Essentially, the array for this site is sized to the cooling load of the refrigeration system. And so we don't, unlike solar where you want to maximize the number of panels on a given roof, we just really want to put the right amount of our panels out just to meet the cooling load, and not more. Really, it's you get diminishing returns as you start to add more panels to the system. But in this case, we are doing this pre-cooling and subcooling for 2 refrigeration systems. We installed 80 panels at this site, and before we installed these panels, the existing condensers were more or less at the end of their life. But this particular store is slated for a remodel in 2027. And so the building owner didn't want to replace the condensers this past summer because those condensers would become a stranded asset because the next refrigeration system is going to be a CO2 one, and all of this equipment will be removed. And so what we were presenting to them is essentially using the panels to add heat rejection capacity to the condenser cycle in the summer. And then in the cooler times, the condenser has enough capacity. We would subcool refrigerant, adding efficiency to the system, and they can continue to operate until they do their CO2 conversion. And then at that point, essentially, they would replace the heat exchangers with high pressure versions of the same heat exchanger, and then it would still continue to provide efficiency value to the store for the next 10 years or so. The entire lifetime of the panels are 10 to 15 years. But yeah, the first couple of years would be as this booster to the existing equipment. And so here you can see the heat exchangers. We had 2 subcooling heat exchangers, 1 per rack, and then pre-cooling heat exchangers after the compressors before the condensers. But in this particular system, we're subcooling the refrigerant when the ambient is less than 75 degrees, and that gave about 15% improvement to the efficiency of the system. So you're getting more cooling capacity with that refrigerant now, and so fewer compressors actually need to run, and that's why you see less power being drawn by the compressors. And you can see here on the left just the amount of subcooling that we're providing. So it's going to vary as a function of time based on the ambient and the conditions of the site and the load in the equipment. But we're getting between 10 and 20 Fahrenheit of subcooling in a given period when it's running. As a pre-cooler, this is where the undercapacity detail is important. Previously the system's head pressure, the approach to the ambient was much hotter than it had been designed for, because the condensers had, for example, fins had corrosion on them because load had grown over time as they put in new cases, for example. So, previous summers they were seeing an approach with the ambient between 20 to 25 degrees Fahrenheit. It was originally designed for 15-degree approach, and so by adding the panels, we're essentially able to lower the discharge pressure of the system, and essentially the discharge pressure goes down, so it reduces the demand, the power draw, and it improves the efficiency of the system. So much in the same way as if you were going from an air-cooled condenser to an evaporative condenser. We're essentially doing that, but without using water. And then this is still above the dry bulb temperature. We're not approaching the wet bulb, but there's still inherent value for lowering the discharge pressure. So in this case, this was an R404A rack. We lowered the discharge pressure by about 35 psi and lowered the approach by about 10 Fahrenheit. So we have 2 projects that we did with CO2 refrigeration systems. So these are in Texas. One's closer to Houston and one's closer to San Antonio. So the Houston one is in Katy. It's going to be more humid, and then the La Cantera site is near San Antonio, so a little bit drier. But in this particular system, we're only doing the pre-cooling or desuperheating. The condenser in this case is an adiabatic system, so it has some water spraying capability. It sprays water in the summer when it's particularly hot outside as a way to lower the discharge pressure and reduce essentially the discharge pressure when it's transcritical. And so adding the panels essentially allowed the discharge pressure to come down even more, and it allowed the entire system to not be transcritical during certain ambient conditions. So in for example, La Cantera, we actually were able to eliminate all of the transcritical hours at this site over the summer. This is just 2 particular days with the panels on versus off, but you can see adding the panels lowered the discharge pressure relative to when the panels were off, and that had implications on power usage. And for these particular systems, they have some issues with control stability with CO2 systems as they go transcritical or as they transition from subcritical to transcritical, but we're able to prevent those issues from occurring. And then in Katy, which is a slightly more humid environment, or a much more humid environment, we're able to lower the amount of transcritical hours. So over the course of the summer, you can see here, at a given ambient, how much we were able to reduce the number of transcritical hours at a site. And so the curves on the left are, again, two similar days. You can see the lowering of the discharge pressure and associated power reduction, and fewer number of hours where it was transcritical for this particular day. And so what we did is we binned that data over the year, over the summer specifically, to show a reduction in these transcritical hours. So when it's really hot outside, we're still seeing transcritical behavior with our system, but certainly far fewer hours than you would have otherwise. In this particular site, since these are adiabatic condensers, we're not necessarily saving water. The spraying is happening at the same frequency and same rate with our system on versus off. But the benefit of having our panels there is that you can get closer to the wet bulb. The refrigerant can get closer to the wet bulb essentially, and so that's reducing the number of these transcritical hours and then saving energy and power. In this particular system, there was an evaporative condenser. We have 80 panels. Again, it's connected with refrigeration system. There's a low and medium temperature groups or cases, and the goal for this project was to reduce water usage. Water tends to be relatively inexpensive, and so the ROI for this project is longer, but in places where you don't have access to water, or there are severe water constraints that you're expecting in the future, this can be a way to reduce water usage. And I can get into the specifics there. But for this project, we essentially installed flow meters on the water that went into the cooling tower or the evaporative condenser and leaving the cooling tower. And so we could measure directly how many discharge cycles were on the tower, how much water essentially was flowing into the tower to provide cooling. And so you can see for this plot on the left that there were just a lot more discharge cycles when the array was off versus on, and that the water usage over a given day was reduced by about 30%. And then we essentially correlated this data with the ambient over the course of a year. We're able to show nominally a 33% reduction in water usage when our system was on versus off. And so we created these correlations, and then we're able to come up with an estimate of how much water was saved over the entire year. You'll see more water savings when it's hotter outside, just because the air is hotter and it can essentially hold more water. So we saw much greater evaporation rates during those times, but the impact was significant for this particular store. So this is a case study that we've developed with data centers, or 4 data centers. So in this particular system, we're using the panels. So the baseline system is a chilled water system with air-cooled condensers on the chillers. And so, and there's dry coolers, which are providing some economization in the winter cooler seasons. What we're presenting is using the panels to replace the dry coolers in the system. And essentially the panels are able to provide direct chilled water in the winter or shoulder seasons, so fall and spring. And then when it's hotter outside, we're subcooling the chiller to provide efficiency. So we ran essentially an 8760 model. This is for a site in North Carolina. But the difference between, say, using our panels and a dry cooler is we were able to add about 15% more hours out of the year where we could economize the system. And that's really driven by the fact that the panels have a much lower approach to the ambient. When you have a fan, you need to have a fluid that is above the ambient. And essentially with these panels, we can cool fluid up to the ambient or even below the ambient. And so there's just more hours where we can economize in the year. We saw a 9% reduction in peak power. So this is going to be during those hottest hours of the year. The chiller was using 9% less power. And then over the entire year, a 39% reduction in energy use relative to the chillers. And that's really driven by reduction in fan energy and not using the chiller for a larger fraction of the time. And so you can see a summary table of the cooling load, how much power was used, and how much energy essentially was saved from cooling. And so we were able to take the PUE for this particular facility from, I think, 1.15 or 1.16 to 1.1. And so data centers are different from these cooling systems and the refrigeration systems just because they are much bigger. So this is for a 700 kilowatt cooling load at a 1 megawatt facility. But you essentially need a lot more panels. It's nominally 2,000 panels in this case versus the 80 panels I mentioned for the supermarkets previously. In terms of economics and how we think about them, each project is unique. It depends on the existing cooling equipment, but generally what we're presenting for stores or sites where you have underperforming assets like a condenser, so instead of replacing that condenser with a new one, you can install our system, and it's going to have 30 to 70% less capex than say replacing the condenser. This is eligible for an IRS tax credit, and so there is an opportunity to also reduce that or improve the whatever it is as a baseline if you add thermal storage. And I can answer questions about that if that's of interest. But this would be tanks of water that the panels would cool at night, and then that would be deployed during the day. This is a somewhat new concept that the IRS essentially released language on within the last 2 months, but it's under the Section 48E ITC tax credit. The system also saves energy, so it's reducing energy use for the cooling system, and so it's less capex. It saves energy. You're going to avoid issues with the refrigeration system in really hot times, avoiding, for example, refrigeration contractors having to come to a site. You're avoiding food loss if the rack shuts down as well. And then the third sort of way to think about it is it's compatible with whatever cooling system comes in the future. So right now there's a lot of flux happening with cooling systems. If you think about the transition from high GWP refrigerants like 404A and 410A to lower GWP or ultra low GWP refrigerants, there are a lot of changes that need to happen to this cooling equipment. And so because we only interface with cooling systems using a heat exchanger, it's easy to swap out that heat exchanger in the future if that's a change that is going to happen out of site. And so you don't have a stranded asset issue like you would have today with for example, HFC cooling systems. So in terms of when we think it makes sense to have panels, we're not going to put panels on systems that don't have cooling loads throughout the year. Really, I didn't really mention this, but we want to focus on cooling systems that have loads not only during the day, but also at night, not only in the summer, but also in the winter. And that's because the panels can reject heat all the time. And that's how we can get more energy savings in our panels than say solar panels. And that's really driven by the fact that we can cool at night, and you can only cool at night if you have a load at night. And so that's why having a refrigeration system or high occupancy building where cooling is persistent, or a data center is the focus in these case studies. And so they're going to make sense when you have condensers that are degraded, underperforming, but still have some useful life. They're not leaking, for example, and we can add capacity. So instead of replacing a condenser, we can add an array of panels. It's going to cost less, and it will have this efficiency benefit over the lifetime. You have, for example, issues where refrigeration or cooling systems are underperforming. They're derating because it's hot outside. You have a refrigerant conversion and you've lost capacity. So these are sort of scenarios where you might want to put panels in. You have high power usage if you're using CO2 as a refrigerant, for example, in supermarkets or cold storage facilities, or if you want to just save water, which is becoming more and more important as things get water stressed from rising temperatures. I appreciate your time. I don't know if there's going to be an opportunity for questions, but John, if you have any questions that you want to ask, or if you want to.
Oh yeah, there's plenty of questions. I want to start. So one of your last slides was consider using SkyCool if, and then you had this list of whatever.
Yeah.
Well, yeah, why don't you go to the next? Oh yeah, there it is. I think that you might be missing one. Isn't it just a good energy conservation measure? If you're looking to save energy, let's say at a building with a lot of air-cooled chillers, or maybe a data center or something like that, isn't this just something that someone would want to retrofit to save energy?
Yes, absolutely. Yeah. And so this is an efficiency measure as well. What we find is that essentially there's more value that we can provide if you have a stranded asset concern, or you have power limitations, or what have you. But yeah, yes, if you just want to save energy, this is essentially a way to do that as well.
So it sounds like you're used to talking to the building maintenance people and not the energy efficiency people.
Yeah, and I think that's predominantly, we are a startup, and so our costs are high. We're doing things in small volume, and so it's often challenging to have things pencil out with just efficiency alone, especially when you're talking to folks in, for example, the Midwest, or in places where electricity is, 6 or 7 cents a kilowatt hour. In California, obviously that math is very different because the cost of electricity is much higher. But yeah, we want to create a product that we don't just sell in California and in places where there's incentives, for example. And so the capacity value proposition is one that we're very focused on, for sure.
Okay, so here's a related question then. So in the LA area or in the Bay Area, I don't care which, but LA would probably be better. What more or less would be a payback range, ballpark payback you would expect? Let's say if it's a data center, or let's say it's a supermarket, or let's say it's a hospital with a lot of air-cooled chillers in one wing or something. Or with a kitchen with a bunch of refrigeration, what kind of payback range of paybacks would you expect?
Yeah, so if it's an avoided condenser replacement thing, it would just be cheaper. So I guess the notion of payback is more on a capex thing. If it's just strictly efficiency, then it would be 3 to 7 years, depending on how big the system is. So like solar, there are fixed and variable costs with an array. If you have a small array, those fixed costs get spread out over fewer panels, and you can think of energy savings as proportional to the number of panels. And so a bigger array will have a shorter payback, essentially.
Okay, and so this payback you're just talking about, the 3 to 7 years, that is not about capex stuff and replacing condensers. That's just energy savings alone. Is that correct?
Yes, and it's going to depend on the cost of electricity and the details of the cooling system.
Oh, absolutely. So we were just talking about LA. Yeah. LA area where power is what, 25 cents more or less, 22 to 25.
I would say with that, it's assuming that these are persistent cooling loads. This is not going to be building HVAC for an office, where you don't run a compressor that often, but this would be, you're a supermarket, or you're a data center, or a cold storage facility. And this would be strictly for HFC systems. I think for water savings projects, the payback is going to be longer, just because the cost of water is relatively inexpensive. But there's usually other reasons for wanting to use panels if it's to save water. And that's
this crowd is mostly about energy. That's what they think about. And they think, I mean, look, I might be representing you wrong, but I think that we think a lot in payback. Is this thing going to give me a payback of 3 years? If it is, I'm all over it. If it's going to give me a payback of 10 years, not interested. And that's kind of, I think that's how they think in this group. Texas. So Texas is what, 8 to 10 cents a kilowatt hour?
Yeah, it's much harder. Yeah, and it's much harder to sell on payback. And so that's going to be like a 10-year payback. You can avoid capital costs, then it makes the math a lot easier. So for example, we're talking to a supermarket in Texas. They have condensers that they need to replace because they're not able to reject enough heat, but they're also scheduling to remodel that store in 2 years. And so they could spend, $300K on new condensers, or they could spend, let's say $200K on an array, save energy, not replace those condensers, wait those 2 years, have streamlined operations, or at least a facility that doesn't shut down in the summer. And then in 2 years, when they're planning to do that remodel, they can just move the heat exchanger.
Right. Okay. Okay. So then I guess what we can say is this is a good ECM for cases where your electricity rate is high and where there is a lot of sun, not so much fog, and where you have power needs or cooling needs all the time. And that would be like you said, so that's refrigeration, that's data centers, and that was, oh, if you're really cooling all the time.
Yeah,
Okay.
industrial processes are also relevant. Controlled atmosphere, storage, for example. I'm not sure if you would group that into cold storage, but that's an option or opportunity. And it's, it's not just sunny places. For example, projects in the north, closer to the Canadian border are also good in cold climates. You just get more free cooling. So if you have a data center, for example, in Eastern Washington, or a cold storage facility there, you're able to reject a lot of heat when it's cold outside. It's also very dry up in those climates.
That electricity is 4 cents out there too.
But yeah, for sure. So it does become harder from an efficiency standpoint.
But you do have like Minnesota that's as cold, but that's other stuff. Okay, so all right. One other question for me is, you said the system lasts 10 to 30 years. I'm curious, what breaks down? What is it that's what's the weak link?
Yeah, so it's the film. So the film will last 10 to 15 years. Most of everything else in the system will last longer. We're using solar racking, and that's designed for a 30-year outdoor lifetime. And same with the piping. Insulated and jacketed. It will need to be, probably checked periodically to make sure the jacketing is on it. But it's the film, and so you can recoat the panels. The film has an adhesive on the back of it. And that's a process we haven't had to do yet, but we imagine we can start to do in 10 years, for example, for systems, and then you can get more lifetime out of the product. But we expect the cost of refilling would be 10 to 20% of the initial cost, and then you get again another 10 years, 15 years out of it.
Okay, so now I'm going to the questions from the crew, and these crew meaning the people who are listening. These are going to be they're good. They're going to be good questions. Here's one. I was wondering this too, but I just thought maybe I spaced out, and so I didn't know the answer. Have you configured this to work with water-cooled chillers?
We have not. I think that you practically could. So you're essentially just replacing a fluid cooler or a cooling tower. You just need a lot of panels, and so it depends on how much roof space you have. But you absolutely could use this as a dry cooler. Anywhere you would use a dry cooler, you can use this concept.
Okay. If there's a building with 50 RTUs, can you talk about how a general install would need to add refrigerant to each RTU? That is the loop. Okay, does that make sense?
Yeah, so for example, sometimes there's buildings that have like a central cooling tower. There's a water loop that goes to maybe RTUs. Is that the framework, or is it just rooftop units that are air cooled? Say
yes.
A Walmart.
Yes.
I guess either one.
Yes.
Yeah. So for like a Walmart with a lot of RTUs on the roof, it really depends on the size of those RTUs. It may not be the right project for us because we want to have larger cooling loads. We don't want to do panel connections at cooling systems that are less than, say, for example, 40 tons or 50 tons of capacity. You run into this issue where you have high fixed costs. So there's a pump, there's the installation labor for the heat exchanger. If you can spread that out over more systems, that's better. So I wouldn't necessarily want to do a project where you had 50 RTUs on a roof and each one is 10 tons. For that type of project, if it's a warehouse, I actually might, depending on the location, you might want to just put the film on the roof, and that will keep the roof cool. That will reduce the amount of heat that goes through the building. This is a different product, but one that can still reduce cooling loads.
Okay, I guess I'm confused here. I thought that you have, let's say you had 50 RTUs. That doesn't mean you need 50 arrays. You need one array, and then the RTUs can all feed into that one array.
But you will need 50 heat exchangers, or depends on how many circuits are in RTU. Often RTUs will have multiple circuits, and this is not going to be true for every RTU, but let's say you had a 50-ton RTU. There often are 3 circuits within it. So each circuit would need a heat exchanger because each circuit is independent. And so you'll need 3 heat exchangers. And so then that's where the costs start to go up when you have 3 refrigeration heat exchangers, and that's just, it adds more time to the installation. It's for sure possible.
That's good. Would the IRS tax credit is 48 EA1B, apply to chillers, panels, and labor for a new,
So it would apply to the tanks and the panels. And so the language is essentially, and everyone should read this, and I can share a link afterwards, but the language that says it's essentially the equipment associated with cooling the tanks. And so our panels would cool the tanks, and the tanks would then provide the thermal storage capacity for the store, for the site.
okay, so this person was asking, let's say I put in a new chiller system and then I added the SkyCool system to it. Can I use the tax credit on the entire chiller system plus SkyCool, or would it only apply to just the SkyCool?
It only would apply to the SkyCool side. I think there's a language that says you can't use it to
Okay,
reduce the cost of the primary cooling system.
that was a really good question.
No, I mean, I think the IRS language is written in a way that it's very general, but it's also, kind of opaque. But they do talk about that specifically. They don't want to use this tax credit for a chiller system. It's for the thermal storage component. And so I think if you had a heat pump cooling the tanks, perhaps that heat pump that cools the tanks might qualify, but the primary cooling system would not qualify for that. I don't know if that helps at all.
Here's another one. I have several cooling towers that are maxed out. Have you ever added panels to solve condenser water problems like this?
Yeah, and so those are the types of systems that we're trying to identify, so we can provide more capacity. So instead of adding a new condenser and replacing it, we can put out an array of panels to do that. So those are the projects that we're looking for today. And so I don't know if my email is available to anyone, but you can go to our website, or my email is eli@skycoolsystems.com. It would be great to learn more about those types of projects.
Or why don't you go to the very last slide? There's something that's it says questions and it has a bracket. It says, yeah, that one. You can email to us also, and we'll pass it straight on to Eli if you guys want. And so you can do that, and we'll pass it right on to him. Here's another question. I told you you're gonna get a question.
Sounds great. Like crawls all over again.
These guys ask questions. They're good, especially when they're hard. I mean, when your topic's involved like this, then they'll go. So okay, we work on chill water with cooling towers and flat plate heat exchangers in winter.
Yes, exactly. And so that's really what we're doing here to get this economizing. This is a data center example, but it would be true of any type of system, as long as the supply water temperature is lower than what we can provide, is warmer than what we can provide, then we should be able to add essentially capacity to the chilled water system.
Okay.
That makes sense.
Yeah.
And so like an extreme of that is, let's say you're in Minnesota in the winter and you're cooling a fluid that's 65 Fahrenheit, or you want a 65 Fahrenheit fluid. Yeah, in the winter, we would absolutely be able to provide that. I think the challenge is as it gets hotter outside, let's say still in Minnesota, but now it's 95 degrees outside. We're not going to be able to provide 65-degree water. It really depends on what the delta, the return water temperature is relative to the ambient. And so the bigger that is, the more capacity we can provide.
Okay, next one. Is the 8 to 10-year payback in Texas after factoring in the Section 48 tax credit or before?
That would be after. Yeah. I mean, electricity is 5 cents a kilowatt hour, 6 cents a kilowatt hour. It's just always hard to have paybacks, and so that is exactly why we're more focused on these capacity situations where we're not just providing efficiency, but also you don't have to replace a condenser, for example, or you don't have to have this stranded asset situation.
But I would think that you'd have good markets in like not Florida, in California and Hawaii, just good markets.
Yes, for sure. Yeah, and that's just straight simple payback. I think if your electricity is more than 20 cents a kilowatt hour, efficiency makes more sense. And there's utility incentives which you can use to further reduce payback, but the reality is most of the U.S. has much cheaper electricity than California. So I don't know, are most of the people on the webinar from California or outside?
No, they're all over the country. Most of them are on the East Coast.
Yeah.
Okay, is there any application of SkyCool for VRF HVAC systems?
We have not done a VRF system. I think it's more complex, just because the VRF controls are often very complex.
Yeah, I buy
VRF
that.
system, I don't know this, but if for example, the expansion valve is in the head unit inside the building, and you just have liquid refrigerant going from the condenser outside to inside, you may be able to have a heat exchanger there, cool that refrigerant liquid. But I don't know the details of VRF systems and how they're constructed, but it would depend on where essentially the expansion valve is.
Yeah, I think better to start here and then expand out.
For sure.
For now, VRF's out. Okay, yeah, so one other, Len or Larry also mentioned, one of the listeners, he said, yeah, this is also going to work for hospitals that have year-round cooling. A lot of hospitals are cooling all the time.
Yes. So for hospitals, it would, the only other detail I would add is like, it really depends on roof space to floor space. So some hospitals I imagine are, vertical, they're really tall buildings, you don't have a lot of roof space. If it's a hospital that's 3 stories and there's a lot of roof space, for sure, there's more opportunity to put an array of panels in. Yeah.
Does the system work with ammonia systems present in large refrigerated warehouses?
Yeah, so we're actually today working on our first ammonia system. It's in Idaho. It's a potato cold storage facility, but it's ammonia, and so we're going to be, and it has an evaporative condenser. We're going to be same construct, pre-cooling and subcooling the system. So it's subcooling in the cooler times, pre-cooling in the warmer times. But yes, absolutely works with ammonia. The only consideration, or I guess there's a couple differences on the safety process side, but the heat exchangers in that case have to be ASME rated, and so that's just a detail in the design. But yes, should work just the same with ammonia.
Okay, what is the heat exchanger material and configuration for the fluids circulating to the panels?
So we use brazed plate heat exchangers. They're manufactured by Alfa Laval, which is a Swedish company, but they're stainless steel typically, and so they're compatible with ammonia. There's high pressure versions which are used for CO2 when you have transcritical CO2 systems. And those are all sort of determined at the point of design when we start a project.
Are the pumps start-stop or on VFD, and what is used to control the operation of them?
It's a good question. So we have VFD pumps. They're made by Grundfos. They are controlled by sensors that are in the system. So for example, there's an ambient temperature sensor. There's pressure sensors in the system. There's temperature sensors for the fluid. You can see the T icon here. So we're measuring how cold these fluids are, and we control the pump based on all of these sensors. But there is more of a decision tree than like a set of sophisticated logic that's how I would describe it. But for example, we don't want the refrigerant to get too cold, so we'll slow the pump down if it starts to get too cold in the winter. We can direct flow from a subcooling heat exchanger to a pre-cooling heat exchanger, and there's a 3-way valve in the system, so that will direct the flow then.
What controls can you interface with, or do you just use dry contacts, and the controls are by others?
We can do both. The pump is Modbus sort of enabled. And so we control it with a Modbus connection to our platform, and it can also be run with like a, 4 to 20 milliamp or 0 to 20 milliamp or 0 to 5 volt signal.
Okay, can you compare, you mentioned this on your website, but can you compare PV panels and SkyCool panels?
Yeah, so the key difference between, say, what we're doing in solar is just that solar is only going to generate electricity when the sun is up. And so SkyCool can reject heat not only during the day, but also at night. And so when essentially you have a cooling load that's year round, that's when you can save energy, more energy than a solar panel can generate. If you have like a office building with an RTU on the roof that only runs, part of the time in the summer, the efficiency is going to be still the 10 to 15% or 20% number, but it's only going to be a much smaller set of hours out of the year. So the amount of money that you save is going to make the payback, 20 or 30 years. So it's not going to be worth it from a project perspective. But yeah, solar solar panels. We're using the same racking as the solar industry. It's attached to the roof the same way. We tend to use ballasted systems, but in places where you have high winds, hurricanes, and tornadoes, you need to have roof penetrations. There's no electrical connections in our panels. It's all hydronic, and so like the labor is somewhat simpler. We don't have to work with the utility, for example, whereas with solar, you know, you have to have an interconnection, and that can add delays and a lot of cost to projects, especially in places like Texas, for example, where there's, or California, when you have a lot of backlog in these utilities.
Can these panels freeze?
Can they freeze?
Do you have freeze damage?
For sure, Ken. So we specify the glycol concentration. So maybe I missed saying this, but we use water glycol in the panels, and we use the glycol size essentially, or the percentage of glycol is set to prevent freezing from occurring.
Okay. Yeah, I thought it was just one.
Yeah, so we have a project in for example, Minnesota or in Idaho. You know, we have very cold winters, but the glycol concentration is going to be, you know, 45% or 50% to prevent freezing from occurring.
Another question: how about panel maintenance? You might have talked about this, but I'm going to say it anyway.
I have a slide on
panel maintenance, soiling and snow is what he said.
So, you know, cleaning is going to be the primary maintenance thing that would happen over the year. It's going to be seasonal. You know, you need to clean it during dry times. When it rains, that often will clean the panels. But we're using the same folks that would clean an air-cooled condenser. You know, it's essentially a pressure washing system. We're cleaning solar panels, but it's just spraying the panels like you can see here. There are other sets of maintenance that need to happen at longer time intervals. So for example, there's a pump in the system. There are pump seals that need to be replaced. Grundfos, for example, recommends that happen every 2 to 4 years. We have the glycol in the system, which has corrosion inhibitors. You know, we manage the pH in that system, so it's, you know, making sure that the pH doesn't go too high. But you know, it's replacing the fluid every 3 to 5 years. There's, you know, visually inspecting the array. You know, this is out on a roof. There's always things happening on a roof that you may not expect. But you know, making sure that, you know, pipe insulation is still on the panel, on the pipes. That's important as well. And then, you know, that 10 to 15 year lifetime of the film, it makes sense to replace the film if you have a cooling system that's going to continue on in operation beyond it, and you want to continue to use this as an asset. But if you don't replace the film, what's going to happen is the reflectance of the film will start to decrease, which means the performance during the middle of the day and in the summer will go down, but the performance at night will be the same, and especially in the shoulder seasons when it's not as sunny outside.
Okay, so I think that's it for our questions. I want to summarize what I got from my perspective, which is I'm not really an energy engineer, but I kind of am. And that is, this is a good energy conservation measure for places where you have a higher electricity rate. My guess is you probably should consider it at rates of like 15 cents or maybe even 12 cents or more. And where they have bigger buildings with large cooling load that is used all year. So night and day, winter and summer. So that would be refrigeration, that would be data centers, and that could also be large buildings that just are always cooling. Yeah, that's, I think, where it would be a useful ECM. It should be in our ESCO projects that people do. And also energy consultants, I think, should be recommending this more often when they're doing energy audits.
Sure.
Do you want to say any last words before we wrap it up?
No, I think that was a good summary. Yeah, I think the higher cost of electricity obviously drives payback. There's this thermal storage concept which you can qualify for that tax credit, which is helpful from a payback perspective. And then I would say, being able to reduce power usage or prevent the use of water. Those are ways to get non-energy benefits to reduce payback. But I appreciate that this is a group of people that are focused on payback and energy efficiency. So
there's one more question. If we have a project opportunity, who should we contact?
Yeah, reach out to me. We have myself, or you can send the email to John mentioned. You can forward it to me. But my email address is just my name, Eli, E-L-I, and then it's at skycoolsystems.com.
Or you can go to their website. There's a form you can fill out as well
Also
on their
true.
website.
Yeah, exactly.
Yes, I think it's called, was it skycoolsystems.com or is it skycool.com?
Skycoolsystems.com.
Skycoolsystems.com.
Mhm.
Yeah, go there and you'll find some of this stuff. I think there's even videos, right? Are there videos there or is it?
Yeah, we have had a lot of media about ourselves, which has been great. But yeah, there's videos, there's a TED Talk, there's
Oh, cool.
lots of content on how it works and what it does as well.
Cool. You made the TED. Good for you. All right then. I think we're done. Hey, Eli, thanks a lot. You did a great job. Guys,
Thank you.
thanks for sticking around. I hope you learned a lot. I'll see you next month.
Thanks, John. Bye.